Hey, yeah, thank you first of all for the invitation. Really happy to join this amazing event on this very important topic. Already enjoyed hearing the discussion, at least. Unfortunately, I couldn't join for the presentation. I do have 25 minutes, isn't it?
Yes,
okay.
25 minutes.
Okay, just to make sure. So I put together a little a presentation where I show a little bit of our work at Auer and also some research we are doing at TUM. So for those who do not know me, I'm coming from Auer. Auer is an engineering firm which is based in Germany, in Stuttgart and in Munich. We also have an office in New York and in Paris. Sounds like a big firm. We are actually not. We are still somewhere having 70-ish engineers in those 4 locations, specialized on something we call climate engineering. We are doing this now for almost 30 years. It's actually next year, it's going to be our 30th anniversary. And we always called it climate engineering. As I said, it was more about, let's say, developing climate strategies for indoor environments. But something like almost 15, 20 years ago, we started particularly in context of urban design, started to look also in outdoor environments. Since 2014, I'm also a professor at the Technical University in Munich. And so this is my team at the Technical University in Munich at TUM. And I feel really privileged to be able to work on both sides, to work in the academic environment as well as in practice, even though the academic environment certainly became the focus of my work. Climate engineering, what it means, just quickly, we did this installation 2010. We got invited to do an installation at the Architecture Biennale in Venice in Italy. And we had this idea to do an indoor cloud. We did a cloud once before in an indoor environment, and we did this not because we wanted to show that we are artists or anything like this. We did this because we think that doing a cloud in an indoor environment is the visualization of climate engineering. You have to manipulate climate to the extent that a cloud starts to appear. And since you all come from physics or engineering background somehow, you know that you can only create a cloud, you can only, or let's say only water particles in air becomes visible as a cloud. And in order to have water particles in air, you need to have a saturated layer of 100% humidity. And if you have a saturated layer of 100% humidity, you can spray in water and the water cannot evaporate and it starts to appear as a cloud. So that's the idea. Now, warm air has a lower density than cold air. Warm air goes up, that's what we all know. Humid air also has a lower density than dry air. So warm, humid air goes up. So you can have a layer of dry and cold air below. And in order to prevent that the cloud layer is touching the ceiling where you would get condensation, you can squeeze it into a hard and dry layer above and a cool dry layer below. So that's the idea. So the physics behind is actually quite easy and straightforward, but it took us something like almost 4 months of testing and trial and error until we achieved the stable layers so that the clouds started to appear. So now Tetsuo Kondo, an architect from Japan, he designed the space, he designed the ramp where people could walk and experience the different temperatures and humidities within this cloud layer. So here you see what's our understanding of climate engineering. And let's say we usually don't do clouds. It's about comfort, it's about environmental quality in a space. But you can see to what extent where one can really manipulate climate locally so that we provide comfort where people are. Now, jumping on an outdoor environment, I think what's very important is that we distinguish between outdoor comfort and urban microclimate. It's somehow related, but at the end of the day, it's 2 different things and 2 different strategies we need for one and the other. So, by the way, this is a picture from Damascus, which we took in times when there was no civil war in Damascus. in Syria. But you see, it was quite interesting for us to recognize that people live and spend time in an outdoor environment in a climate where you have in summer during daytime every day temperatures around 40-ish degrees. So you really wonder, why do people enjoy the outdoor environment? Something similar we also found later than in Singapore and Kuala Lumpur. In a very humid environment, people appreciated an outdoor environment treated to a certain extent over a fully air-conditioned, overcooled indoor environment. So this made us curious, and we started to dig into it. We were certainly not the first one. I mean, we built up on a lot of research that happened before at several universities. And so then in 2014, our Munich office, Wolfgang Kessling, he worked on this with a team from Austria on this Austrian pavilion at the expo in Milan. It was called Breathe Austria. And by the way, it was the only pavilion at the expo in Milan which did not have any air conditioning. Most of it was outside. And so the idea was to bring a forest from Austria to Milan to create microclimate and make people breathe Austrian air. So that was the idea. And there was something like 600 square meters of piece of land one could use to bring this forest to Milan. But the intention was to bring let's say, the cooling potential of 1 hectare of forest to Milan. And in order to increase the evapotranspiration of vegetation, we combined this with elevated airspeed and this kind of dry fog system. So adding more evaporative cooling by a mechanical system. That was the idea. And here you see some images of how people appreciate this kind of environment. And then our Munich office went there doing UTCI measurements about the same day, a hot day with outdoor temperatures of about 35 degrees at different positions outside the pavilion and inside the pavilion. Outside the pavilion, there was this main street. I can't remember how it was called, but there was a main street from which all the pavilions were going off, which was covered by a fabric shading device. So position 1 was already in the shade. And so these are the UTC. I don't think I need to explain UTCI, isn't it? Universal Thermal Climate Index. So kind of perceived temperature, but I think in this audience, everybody knows this kind of metric of perceived outdoor conditions. So what we measured in this main street was an air temperature of 34.5 degrees, a relative humidity of 44 degrees, but a mean radiant temperature of 38.4, and basically no wind speed at 0.3 meters per second. So this led to a UTCI of 36, almost getting into the area of extreme heat stress, so just below extreme heat stress. What you recognize is the high mean radiant temperature. So what happens is that this fabric is obviously gets heated up by the sun and then acts as a radiator for the space below. Now, walking into the pavilion, there was still no evaporative cooling, just basically replacing shading from a fabric by the shading of a tree. And you see that the air temperature is a little lower, goes down to 32.5. Humidity, obviously, when air temperature goes down, humidity goes up to a certain extent. But the mean radiant temperature goes down by 6 degrees, still no air movement. And you see from being close to the threshold of extreme heat stress, we almost get to the threshold from heat stress to slightly too warm. So yellow is slightly too warm, green is comfort. And then getting into the pavilion where we have the evaporative cooling and the air movement, the elevated airspeed, you see that the air temperature drops down to 27. We get high humidity because temperature goes down and we have the fogging system. The radiant temperature is a little higher at this specific spot. It's at 34. But then the wind speed, the air movement is at 2.6 meters. So overall, we almost get into comfort. So we are below 28. As we started above 36, there's a difference of 8 degrees, and all 3 locations are in the shade. So don't talking about being exposed to the sun. So you see to what extent one can really manipulate comfort. So this is outdoor comfort. Of course, it also has a microclimate, but it's not about the microclimate of a whole city. We see that in spots, we can create environments where people find relief, where people can cool down. It's not a strategy for an entire city to, let's say, work against climate or change, increased temperature due to climate change or urban heat island effect, but it's a strategy for a local spot, a local cool spot, if you want to say, in a city where people can find relief. Then we did an exhibition just last year from TUM. Birgit Kobas here from my chair, basically together with Atta Chokachian and Sebastian Kurt designed the exhibition. They found this research, which you see here, the source, where there's a prediction of what temperature increase one gonna see in different cities all around the world until 2050. And you see that particularly Europe, particularly the Central European cities, are going to face the highest delta T. And we are talking about something like 4-ish Kelvin in average temperature difference we're going to see until 2050 in Central European cities. Now, you could say this is a cold environment anyway, and so maybe people appreciate. But what we recognize is that particularly in Central Europe, buildings do not have air conditioning. In hot and humid environments, such as Singapore and other places, people have air conditioning. So this increase in temperature leads to a higher energy consumption. In Central Europe, we might get to a point where people suffer from this heat. We see an increased mortality rate during heat waves, all these kind of things. And we might get to a point where people start to install air conditioning on a big scale. So this is certainly something we should avoid. And then at TUM, Atta Chokachian started this, let's say, climate walks, we call it. I'm going to show you a little later. But those were 2 results from Berlin, since the exhibition was in Berlin. Walking through Berlin, and you see the scale here, the upper diagram showing air temperature. The scale basically goes from 25 to 28. And we see a slight increase here in this street. But if we start to display UTCI, then suddenly the scale goes from 26 to 36. And we see a much bigger variation in kind of perceived temperature. You see to what extent, let's say, urban design has an influence on a perceived temperature, which is sun exposure, obviously, but also other aspects. On top of it, when we talk about microclimate, this is now a temperature diagram for the city of Munich, where we took just for one day, one hot day, and was not even a super hot day in September, something like in 2018, yeah, 3 years ago. You see that the solid line showing the temperature measurements from Munich Airport. Munich Airport is in the middle of nowhere, so on the land side, and you see the measurements, the dotted line of downtown. So just talking about microclimate and urban heat island effect, you see that the delta is only about 1 degree during daytime peak time. But in this case, 7 degrees at nighttime. The German Weather Institute, the DWD, they have measured in Munich nighttime, let's say, urban heat island effect of up to 10 degrees, 9 to 10 degrees. And the nighttime temperature is our biggest problem. It's not the daytime temperature. People, let's say, don't even recognize whether it's 32 or 33 during the day. But if the minimum temperature, and that was the case in the summer of 2003, when in France, mortality rate in this hot period really increased around nights where the temperature in downtown Paris did not drop below 30 degrees. And we rely on, in Central Europe, we rely comfort in terms of thermal comfort, we rely on cold nighttime temperatures or cool nighttime temperatures so that we can open the window and cool down our apartments so that they can stay cool over the course of the next day. But when we have a temperature which does not drop below 25 degrees or even 30 degrees in a city, in an urban environment, then we can't have nighttime cooling. And this is when people start to suffer, when they don't find any relief at nighttime when the city stays hot. So this is why we started this climate walks, to get a better understanding of urban morphology and outdoor comfort / microclimate, and how you saw in this example of Berlin, the extreme variation, which is mainly based on urban morphology. So it was getting an understanding how urban morphology really influences microclimate. And here you see two examples. This is again from the exhibition that we had in Berlin. The upper picture shows Rome, and I don't even need to show measurements to one can really feel that this is a very comfortable environment, whereas the lower picture showing Berlin, and one can feel and see how this space is heating up by the sun over the course of the day and storing this heat into the nighttime hours. So this is Atta Chokachian in Berlin with our backpacks, which we use to do the climate walks. So here, this is what we measure. We have a GPS tracker so that we know where we are. We measure air temperature, mean radiant temperature, air movement, and humidity, as well as a couple of environmental parameters such as fine dust, etc. And then later on, post-processing, we get all the data into a grasshopper routine so that we can visualize them here again. And then also at a certain point, we started to measure skin temperature to also better understand the physiology of people. And we have an app. So by the way, we did this together with the university, with the Chinese University of Hong Kong. They started this climate walk, so it was not our invention. We picked up on it. And then together with the University of Hong Kong, we developed this app where people also give a response at certain spaces, locations, how they perceive the conditions. So we have the psychological, the subjective response, we have the physiology by the skin temperature, and we have the environmental data, and try to correlate them with the urban morphology. So those are places where we already did climate walks in context of summer schools, etc. It's always a lot of fun. This is a result of Genoa. This is the tour we did. We walked in Genoa. And then this is UTCI. And you see again a big variation. You see here where we go down to something like orange, which is somewhere getting into comfort, slightly too warm, something like 25, 26 degrees. Here we get into comfort 24 degrees, whereas we have other locations here where we are, let's say, slightly warm or warm getting into heat stress. This is the mean radiant temperature only, so we get the individual parameters so that we can better understand what is contributing to the problem we have. The wind, you see that we have higher wind speed up here in this street, which leads to the lower UTCI temperatures up there. And then you see the result. There is a spot at the waterfront where you're exposed to the sun, which obviously leads to heat stress. A surprise for us was to see that this is a situation like here, where we have really good comfort conditions. The same we have seen in places like Rome, in places like Seville, that this old, let's say, medieval fabric, urban fabric, provides really good comfort, provides really good conditions, really good microclimate conditions, works really well. This self-shading effect in combination with thermal mass exposed to the outdoor environment, but thermal mass which do not heat up by the sun, which is not exposed to the sun. So then we started to also look at sky view parameters so that we get a better understanding of sky view, can relate it to sky view with sun exposure. And then in Singapore, we started to also measure skin temperature. Here, different situations in Singapore. Sorry, I have to speed up a little bit, make sure I stay within my 25 minutes. And then we still try to get an understanding of skin temperature. So far, what we see is that there's a difference between people which acclimatized already and people just arriving. Someone who just arrived in Singapore and did a climate walk and measured skin temperature the first day, you see something different than you see the following days. That was interesting. But also we see a slight difference between male and female. We did not have enough data to really, let's say, getting to a point where we have a clear conclusion, being able to publish it, but we still work on it. And then coming back to Transolar, we worked with TVK Architects on the redesign of Place de la République with Martha Schwartz doing the landscape. And I think what's interesting about Place de la République, I mean, I think you already had this discussion about reflectivity of surfaces. On the left side, you see Place de la République before it got remodeled, on the right side after remodeling. What's interesting, I mean, you can discuss and debate whether it's the right approach to have a bright reflecting surface. It's certainly to a certain extent counterproductive for outdoor comfort. It's supportive for microclimate because it doesn't heat up as much by the sun. But what you see is that before remodeling, Place de la République was completely surrounded by traffic. And you almost killed yourself just getting onto Place de la République. And then buses even crossed Place de la République. And so because of the remodeling, traffic got cut off here. And so the traffic now has to go around Place de la République so that people can get onto Place de la République and really enjoy it, and then combine this again with evaporative cooling to create a place where people again find relief in a hot period, in a heat wave that is coming. I think what's interesting is, in this case, it's about, let's say, materiality, it's about evaporative cooling, et cetera, Very often we talk about vegetation as a climate adaptation strategy. I already heard that you also talked about canopies. However, whatever we do, and then this is a very good example with Place de la République, there is suddenly a competition with, let's say, car infrastructure. We have only one public realm in our cities. And as soon as we use this public realm for climate adaptation strategies, we compete against other uses, and particularly against car infrastructure, against car individual mobility. And that's, let's say, a big debate, a discussion we're gonna have over the next couple of years, maybe decades. And I always say, like, every particularly Central European city, maybe every city in the world, but you have seen the diagram of what increase we can expect in Central European cities. All Central European cities, in my mind, should have a master plan, how they want to adapt to, let's say, climate change, to an urban heat island effect, how they want to minimize this nighttime temperature delta, and where they have to create cold spots, like pocket parks, neighborhood parks, where people can find relief. So that's why I always say we need to distinguish in terms of strategies for outdoor comfort and strategies for microclimate. A microclimate in Central European cities is mainly related to nighttime temperature. Here, this is the final mood image of the fact that I'm convinced that this has a potential to provide better cities, better environments, which people are going to enjoy. Thank you very much.
Perfectly on time, Thomas, as usual. Thank you so much for sharing those exciting projects. During tomorrow's roundtable discussion, we'll be joined by Piero Pellizzaro from the city of Milan. So I hope we can ask him about how Milan is tackling the debate between climate adaptation infrastructure versus car infrastructure, because I know that that's a very heated topic in the city of Milan. We have some time for questions, but before we open the floor for the Q&A period, I want to hand over the virtual stage to Marika. The floor is yours for the next 10 minutes.
Thank you, Emma, and good afternoon, everybody. My name is Marika Tomasi. I'm the ESR number 6, and I'm working on climate responsive systems at the urban scale. This afternoon, I'm giving you this presentation about a user-centered measure for outdoor spaces. And I'm showing with pleasure my supervisory team from the University of Kent, Professor Maria Nicolopoulou and Dr. Giridhara Ranganathan, while from the Carlo Ratti Associati, we have Juan Carlos Romero, Monica Love, Andrea Cassi, and Antonio Atripaldi. So let's start with the problem. Climate change taught us how hard people can be hit by heat waves and exceptional climate conditions. So I believe that ensuring accessibility to comfortable and healthy outdoor spaces is becoming increasingly urgent worldwide. And this is the problem my research wants to address in the bigger picture. In this slide, I'm showing you 2 examples of climate responsive solutions. We have an artificial device that was designed by CRA and was installed in Milan, where I took this photo. While on the right, we can see a tree, which is the most immediate example of device that is able to change its shape, its properties based on seasons, so based on climatic conditions. But how can we move from solution to the concept of system? Let's start from considering the fact that climate impacts on environmental conditions of cities, and this is being well established by research. And so we can say that it affects the people, so the users. Installing climate responsive solutions can be beneficial for the users of the city because it can improve their outdoor experience. So if we consider climate devices and people, they form these climate responsive systems that need to be implemented in cities. And this is the system that I want to my research to focus on. So the research addresses the need for a methodology to locate climate responsive solutions in outdoor urban spaces, the opportunity to adapt and modify the spatial configuration based on people's needs and temporary issues such as the social distancing that was brought by the pandemic. I think it's key, and this is the final goal of the research. The research focuses on solar radiation, and there are several reasons for that. Let's start from health risk due to excessive solar exposure, especially in summer, impact on thermal comfort, as already demonstrated by my colleagues. Its directional nature that leads also to be able to manage the solar radiation component for upscaling purposes when we're working with urban morphology. So the final design goal, let's say, of my research is to create flexible outdoor spaces that can respond to the different solar position. And in this slide, I'm reporting the different solar positions on a yearly basis in Milan. The second part of my presentation, I want to show you a case study that I'm using to explore this methodology and to better assess it. This is a new development in Milan. We can see some buildings that are mostly offices, and we can see an elevated plaza, a square at the center of the buildings. So I started by simulating solar radiation. This map, I think, is already quite informative. We can see the areas that are mostly likely to be exposed to solar radiation on the 21st of June. We can see the shadow, the screen, the effect of trees, for instance, at the center of the plaza, but we can also notice how the shadow of the buildings changes, for instance, during the hours of the day. So I think, as I said, this map is already quite clear climate information that can be implemented in the design process. But I also think that we have to translate this information and we have to build a bit on it from the designer point of view. So the question that is moving my focus to the user experience is, what does climate mean for users? So what can we learn from this map, and what can we, how can we connect climate and users in the outdoor spaces? So the chosen angle to include this user perspective in urban design is walking time. You can see here I overlaid the master plan with a grid, with 2 grids actually. They correspond to 2 different walking speeds. I define them through literature review, and they refers to different level of physical abilities, because the pedestrian can have different level of physical abilities. This grid enables to evaluate, to measure the space actually by the user point of view. So to evaluate, for instance, how much time is needed to cross the master plan or to go from one point to the other. And if we can overlay this grid, for instance, with the solar map that I showed before, we can also evaluate how much time a pedestrian spends in uncomfortable microclimate condition, for instance. And this is a valuable information, in my opinion, for urban designers. So from the really designing point of view, I started highlighting the hotspots of the area, as well as the accesses to the elevated plaza. And I distinguished them between stairs and ramps because of the different level of ability I was talking about. This allowed me to hypothesize some lifelike paths that users would take in experiences this outdoor space in particular. And this is the result that I came up with. I'm going to show to you 2 different user experiences that I simulated. The first user experience scenario, it's a pedestrian that is taking the stairs. In fact, it's starting from southeast. So he's taking the stairs, he's crossing the plaza, going to the restaurant, and then is walking toward the forested area. I estimated a time of 3.5 minutes, and we can see that by the overlapping the solar radiation map, as I was saying, we can consider this path quite homogeneous in thermal diversity. So we can see that there are areas that are really exposed, areas that are screened, for instance, by trees, and we can make consideration about also thermal comfort of this pedestrian in this specific user experience. The second user experience scenario is an old pedestrian. So he's accessing the elevated plaza through the stairs, through the ramps. So we can see that it is taking the ramps from southwest and is reaching the elevated plaza, and then is crossing the area to go on the other side of the new development. In this case, we can see that there's a first part of the path which is exposed to solar radiation, while the second part we can see the screening effect of trees. We can, it's for me at least, it's really interesting to imagine these 2 different experiences, the thermal condition of the users while they're experiencing this path. And I think that through this point of view, through this angle, we can also make design considerations. We can understand where to locate climate responsive solution. We can test configurations, and we can also understand in different seasons, in different time of the day, of the year, whether is needed some screening devices, for instance, temporary intervention, or if the building morphology also need to be adjusted. So the final goal of the research, what's next? The final goal of the research is to provide a protocol for urban designers and planners to integrate climate responsive systems in master planning. This will be the result of an assessed methodology to upscale the solutions to the neighborhood and city scale. So I showed you today how I started from the climate responsive solution, and I'm trying to understand where to locate in a neighborhood, at a neighborhood scale in a master plan based on the user experience. The final goal, in my opinion, is to understand which areas of the city need urgent interventions, for instance, what are the most used by user experience, or where we want the users to go. And I hope to provide this tool for designers. I hope to provide a useful tool also applicable in practice. Thank you for your attention.
Thank you, Marika. Well, thank you for a great presentation for the symposium, for bringing your mind and your talents to Carlo Ratti Associati project, and to a citizen of Milan for bringing climate adaptation solutions to a city that is getting hotter and hotter each year. We have a number of questions from our online audience. My understanding is that Professor Auer has already started to answer them online through the chat box, but maybe I'll read one or two of them aloud and try and expand on them. The first comes from Navid, who asks, the Australian pavilion was designed in 2015. How would you design it today? How would you improve the design? And maybe if I can add to that question, more generally, when we're talking about urban scale or city scale interventions that maybe take many years or many decades. Philip Ram this morning presented a master plan for Milan that is 15 years in the making. How do you design for such a far off future and for such a dynamic context? Perhaps the client who hired you to do the work changes halfway through, or the public administration of the city moves on and another one comes in. What are the challenges associated with designing long-term and big in scale? And how do you design for a future where perhaps technologies that are only now nascent will become commercially available 5, 10, 15 years from now?
But first of all, coming to Navid's question, I think first of all it was Wolfgang Kessling who worked, who supported the design team for the Austrian pavilion, and so it would be a question we should ask him if he would do something different today. I think it's still a valid and good approach, and we tested this approach, and not only tested, used this approach also in human environments in the meantime. This combination of, let's say, elevated airspeed and evaporative cooling, and we see that it works really, really well, and we can really manipulate locally where people are climate to a big extent and really provide comfort. So I think it's still a very good solution, and it's still a super amazing and interesting, super cool pavilion they have built at the Expo in Milan. The Breathe Austria. In terms of timeline, that's an interesting thing. So very often we show this kind of things like on an expo. Now the next expo, we also involved with 2 pavilions in Dubai, where we can use such an expo really to test strategies, climate adaptation strategies in outdoor environments. But if we think of urban design, we started to work on bigger urban design projects already 15 years ago, and none of them are developed to an extent where I can really show a good example here. Those urban design projects are really, let's say, on a time scale, which takes almost forever. Once an urban designer said, designing the city is the design of the unfinished. And I think coming from building design, we really have to learn this, because in building design, sometimes things take very long, and things can take up to 10 years, but we design a product. Which is finished at a certain point. A city is never finished. So a city is always in flux. So the question really is, to what extent are we really going to design a product? To what extent should we really design, let's say, a specific climate adaptation strategy? Or isn't it more about having, let's say, a methodology, how we can create adaptation at different locations? Like, for instance, nobody expected that we have a pandemic like Corona. And in the city of Munich, many people fight for years and decades that we turn parking slots, park space, into something else. Now with Corona, all of a sudden, 7,000, I think I was reading the number, 7,000 parking spots disappeared for, let's say, restaurants. They have, with, let's say, trees, etc., have a nice outdoor seating area. All of a sudden, like this, 7,000 parking spaces disappeared. Maybe we need these kind of events. Maybe to a certain extent, Corona was helpful as a catalyst to make things happen. But it's, again, it's probably less about we need a tool set of strategies. And right now, what I see very often is that cities are desperate, and the tree, Professor Santamuris already talked about the limitations of trees. And let's say water demand is one of the limitations. And so the only focus we have right now, and many cities have, is to say we need more trees. How many more trees? Nobody really knows. So we need to have a tool set. We need to have more science. We need to have a better understanding. We need to have a toolbox. We need to give cities a toolbox of things. And so that over time, when things change, they can always adjust their master plan, their strategies, their climate adaptation strategies.
Thank you, Thomas. I won't quote you on thanking coronavirus for, for speeding up the adaptation of outdoor spaces.
I said thanks to coronavirus.
I have a question for both of you, but we can start with Marika. Both of you touched on it already a little bit in your previous presentation. At CRA, we often start design process from the user's perspective. What is the user experience? And that often involves considering who are the different user archetypes. So you mentioned walking speed, ability to acclimatize, gender. What are the different users that you typically consider when you're doing the design process? For instance, I'm Canadian, so I grew up in -50 winters, but I have a terribly low tolerance for cold. I wear the same winter jacket that I wore in Edmonton, Alberta at -50, at -2 in Italy. But for heat, perhaps I have 30 years of cold stored in my body, and therefore I manage it better. So what are the different typologies of users? And how do you design thermal comfort for different type of citizens?
Thank you. So I start. For the moment, I just focused on the ability to walk, the walking speed, as I was saying, because I was interested in how people were using the space, how they were living, and how they were actually experiencing the outdoor space. So it was natural for me to ask myself, okay, but I don't have a standard user, or at least as a designer, I think the design, especially of the public space of cities, should be more inclusive. So it was natural for me to consider different walking speeds, and I did a bit of literature review about typical walking speed, for instance, of also people that have been hospitalized, moms, for instance, with children, and people also moving with wheelchair. I think, so for the moment, I'm not focusing on gender, even though I'm aware of the fact that thermal comfort is changing a lot based on age, based on gender, but also based on cultural factors, based on physical factor, for instance. So this is something to take into account, and I think once assessed, Thomas was talking about the strategy and methodology. I think once we assess a methodology to include users with different users in the public space, then we can really, let's say, play with this concept. We can play with this methodology and make our cities more and more inclusive.
Thank you. Thomas?
Yeah, I would not say that we look at different user groups, because I think there's still, at least I'm not aware of any research that is really distinguishing between different user groups. Let's say some UTCI, for instance, or any other perceived temperature calculation maybe there's something exists I'm not aware of. However, but what I think we have to be careful, let's put it this way, because right now we all look at this extreme heat events. And however, I mean, Emma, you already said, particularly in Central Europe, like Northern Italy and upwards, the cold season is still longer than these heat waves. So it's still, let's say, if we think about all year long, we still, let's say, on a statistical perspective, increasing outdoor comfort more when we provide wind protection. So this is something we should not forget. So we don't want to have drafty spaces from September until the end of May, and then it starts to become beautiful for 3 months a year, but it's unbearable for 9 months a year. So we have to consider the different seasons. We have to take wind, particularly in a cold season, in colder environments, wind is your enemy, and we should not forget, and so take this into account.
Well, unfortunately, that's all the time we have for today's session on climate responsive design. I didn't manage to get through all the questions, but luckily tomorrow we have a roundtable discussion for exactly that purpose. So we'll collect the questions that were not answered today and hopefully collect more. So stay tuned for our session tomorrow at 1:50 p.m. Central European Summer Time. We're now heading into a short break before a public debate. If you like what you heard here today, please check out Soloclim's website, soloclim.eu, and sign up for our newsletter at carloratti.com. Thank you, everyone. Thank you, Thomas. Thank you, Marika.